Hello, everybody. Welcome back. So, hopefully, I think we can do it. This will be the end of the material. So, here we go. Double integrals in polar coordinates. So, just briefly, we've just seen how to describe curves and regions in polar coordinates, and we'd like to use that to our advantage to compute certain double integrals. Okay, so here's the idea, right? So certain double integrals are complicated because of S. Okay, and it turns out that we have a trick to rewrite the double integral if we have a representation of S in polar coordinates, which might make the integral easier. So often, or sometimes I should say, S has a nicer representation in polar coordinates, and so we'll see how to convert the integral to use this. Okay, so that's the main idea. So just to go through a few basic examples again and to try to illustrate where this is going. So let's just a couple of reminders. Take, for instance, the disk of radius 1 centered at the origin. Right? So if I describe this in rectangular coordinates, what does it look like? This is the set of all xy such that the distance from the origin is at most 1. So x squared plus y squared between 0 and 1. Which is not so bad, but okay. But in polar, this is actually much simpler, right? So how do I describe the points at distance 1, at most 1 from the origin? So the angle could be anything from 0 to 2 pi, and r is between 0 and 1. So this is the set of all r theta, such that theta is between 0 and 2 pi, and r is between 0 and 1. So notice that this is actually a rectangle in polar coordinates. Okay, so if we knew how to reinterpret the integral over a disk like this, we'd get an integral over a rectangle, which is possibly much simpler. Okay, so here's another one. Let's say I take the following region. S is the set. This is in rectangular coordinates. The set of all xy such that x squared plus y squared is between 1 and 4, and y greater or equal to 0. Okay, so what does that look like? Well, you see, it's not hard to see that this will be the following region, right? So you take the disk of radius 2, the disk of radius 1, you remove the smaller disk and you take only the upper half. Now in polar, this is also very easy, right? So the angle is between 0 and pi. And this is the set of all r theta such that theta is between 0 and pi. And what is r is between 1 and 2. So again, a polar rectangle. Okay. And finally, here's another one. So of course, we can't really expect everything to be a rectangle in polar coordinates. That's certainly not true. But there are still regions which are extremely difficult to describe in rectangular coordinates, which are fairly simple in polar. We saw that last class, right? So here's one. That's the last thing I did last time. So it's one leaf of the 4-leaf rose. Right, so I'm going to use this one, this guy here, right? So if you remember, the bounding curve was r equals cos 2 theta. So if I want to describe the points here, if you remember the analysis, I'm going to be reusing this example today, right? So this can be seen as the set of all r theta such that, so the angle goes from minus pi over 4 to pi over 4. So you have to go back to the analysis we made last time. And what is r? Well, it's for a fixed angle, it's anything from the origin to the bounding curve, so 0 to cos 2 theta, like that. Okay? So you see, this is not a rectangle in polar coordinates because the bounds for r are not constant, but it's actually type 1. It's the same as type 1 that we saw, right? So this is type 1 in polar. Okay? And in rectangular coordinates, well, it is theoretically type 1, but to write it down is just, it's extremely difficult. So we're going to get things that we can't integrate. So what I'd like to do now is to define what I mean by type 1 in polar, and then give you the theorem that tells us how to integrate over these regions, and then I'll do 3 examples, and that'll be it. Okay? So, so here we go. What's a type 1 polar region? So in general, here it is. So the region S of the plane is, I mean, it's type 1, type 2. There's no orientation here. This is in polar coordinates, so it's either type 1 or type 2 or both, right? In polar coordinates, if it has the following description. So I'm going to draw it, this sort of a generic, but as you saw, I mean, it could have many different kinds of shapes. All the previous ones that I did were like that. But roughly speaking, what we have are 2 bounding angles, okay? So let's say theta equals to alpha, theta equals to beta, okay? And then we have 2 curves which limit the radius. So we'll have something like this, something like that. Now again, think of the leaf, that the thing might loop back on itself. That's possible. So this is the graph, or the curve, I should say. R equals, let's say, h1 of theta. And this one would be the curve R equals h2 of theta. And the region is everything here. Okay, this is S. So S is the set of all r theta such that Theta is between alpha and beta. These are two constant values, fixed values. And once you fix theta, then R can vary between the two values depending on theta, H1 of theta, H2 of theta. Okay, now we need to impose some conditions here. Okay, so here you have to be careful. And again, I'm not going to try to fool you on the test, but in theory, you'd have to be very careful in checking things. Okay, so next year when you're doing, if you're doing engineering, for example, or doing calculus, some program, you might have to be very careful with this. So the angles that you choose, you don't want to go looping several times because this is going to mess up the value of your integral. Okay, so the values of alpha and beta have, you have to be careful with adding 2 pi's. Okay, so what I mean by this is that the distance between beta and alpha cannot be bigger than 2 pi. That means you're going once or more, twice around, too many times. Okay. The other thing is, and that's really important, that when you're describing this, so I mentioned that we can interpret negative r in polar coordinates, that's fine, but when you're describing a region like that to integrate, you cannot use negative r. It has to be always greater or equal to 0, okay? So the functions h1 and h2, right, have to be greater or equal to 0. Okay, you don't want to have to deal with negative values of r. Okay, and these functions should be continuous. That's the same requirement as we had in the rectangular case. Okay, all right, that's for all. Okay, so r greater or equal to 0. And you don't want the angles, you don't want to repeat things, okay? All right, so if you look at the previous 3 examples, they were exactly of this form, okay? So C3 previous examples, okay? So far, so good? Yes, very good. Okay. Let's keep this here. Okay, so here's our theorem. Okay, so this is, if you remember in Cal 2, the substitution rule, okay? This is an analog of the substitution rule. In fact, there is a very general theorem for double and multiple integrals in general, which is the change of variables theorem. This is a special case of it, and the substitution rule you saw is also a special case of it. Okay, it does look a little bit like it, but here, because we're dealing only with one very special change of coordinates, which is polar coordinates, you might not recognize the substitution rule, but I'll try to explain briefly. Unfortunately, I can't do all the details here, so I'll just try to give you a feel for it, but the key point here will be to know how to use it. Okay, so the following is a special case of the change of variables theorem. And so is the substitution rule. Substitution rule. Seen in Cal 2. Now, the substitution rule in Cal 2, you probably used it most of the time with indefinite integrals. This is the definite integral version. Okay, so here it is. So this is change to polar coordinates. Okay, so if f is continuous on S type 1 to polar as above, so I'm going to use exactly the description that I gave you just before. Then the double integral over S of f, which is usually what we want, right, can be computed as follows. So now what I'm doing is I'm using the description of S in polar coordinates. So the integral is going to look like type 1 type of computation that we made, okay? So it's the integral from alpha to beta, integral h1 of theta, h2 of theta. Now what's inside? I'm switching the coordinates. So x is going to become what? Well, r cos theta, and y is going to become r sine theta. That's the way we convert from rectangular to polar. And now here is the thing that's really important. There's a factor r that has to appear here. If you forget that, you're going to be, it's going to be painful, okay, and wrong. It's a bad combination. Okay, so this is how you can compute an integral if you have a relatively good description of the region S in polar coordinates. Now, this doesn't mean that you have to use polar coordinates, right? It might not be the right way, but sometimes it's the only way, okay? So now I'm just going to make a couple of quick remarks about the R so that you, so what's this thing? Okay, so a couple of comments, and then I'll show you how to use it. Okay. Okay. So the first thing, so recall that when we're switching from rectangular to polar and vice versa, oops. This is how we go from one to the other, right? Okay, so then that makes sense. I'm replacing x and y by r cos theta, r sine theta. That makes perfect sense. Okay. Now, what about the factor? Okay, so what does that mean? Where does it come from? This is a bit difficult to explain. There are a couple of ways I can do it. Let me just mention one thing. Maybe it'll not convince you because, but here's the idea. Suppose that you take in the XY plane a small rectangle, right? Think of delta X, delta Y, right? So you take a small rectangle of width delta X and height delta Y. So it has area delta X, delta Y, right? And it doesn't matter where it is, right? So you can move it around and it always has the area. So wherever it is. Okay, obvious remark. But now, suppose now that I look at what happens in the r theta world. Suppose that I take a polar rectangle, which is delta r by delta theta. So what does that mean? Okay, so this is rectangular, this is polar. Okay, so I take now a polar rectangle delta r by delta theta. Okay, so what does that mean is I have a small difference in theta and a small difference in radius. So maybe it's something like this. Right? So this is delta r, and the difference of angle is delta theta. But you see what happens now is that if I move this thing further out, its area changes, it becomes bigger, right? So it's the same delta r, it's the same delta theta, right? But the area increases, right? So a small delta r delta theta rectangle does not have the same area if it's further out as if it's close into the origin. That tells you a little bit what this r is actually doing, right? It's taking care of this behavior, okay? So that's why. I know it's not, I could expand on this a little bit if you want. There's a nice explanation in the book. Okay, so that's why the factor r. Another way of seeing it has to do with this transformation of the plane. How do you measure how it, forget it. It's just too complicated. It's something called the Jacobian. So it measures how your transformation changes areas. And you could compute, so the partial derivatives of both these functions with respect to r and theta. You get a 2x2 matrix, you take the determinant, and you'll get r. That's how you get it. Okay, so that's a very vague idea of why there's this factor r. Hopefully that will do the job, because I can't go further than that. Okay. All right. So how do we use this? Here we go. 3 examples. Okay, so this is a very, very vague intuition. Sorry. Okay, so that's the best I can do now. Okay, so here we go. Example 1. Okay. What do you mean by factor of r? Okay, so let's go back to the formula. Oops. Here it is. So you see that on the right-hand side, there is the function f is multiplied by r. It's not just a question of replacing every x by r cos theta and every y by r sine theta. You have to multiply the whole thing by r. That's what I mean. You see? Okay. Yes. You don't seem convinced. Yeah. Well, that's what I was trying. Yeah. So that's what I was trying to explain here. So we're saying that the original integral can be converted to an integral in polar coordinates. Okay. But it's not just a question of changing every x to r cos theta and y to r sine theta, because we're computing volumes over a region, right? The way we're doing this, the small delta r delta theta, yes, you can see it, yes. It's related to that, yes. So the way that the polar coordinates work, it's not the same as the way they work in the rectangular world. If you take a small rectangle, when you chop up things in small rectangles, it doesn't matter where the little rectangle is. It has the same area. But if you do it in the polar world, when you're chopping up into little pieces of small delta r, delta theta, depending on how far you are from the origin, you don't get the same area. So you have to compensate to get the right value by this factor r. I don't want to go further than that. If you can, there's a nice little, I mean, sort of nice little illustration in the book that goes a little bit further than what I'm saying. I don't know if it'll be satisfying, but anyway. Okay. So sorry, I have to move on and show you how to use these things. Okay. So here's our first example. So I'm asked to evaluate the double integral over S of 3x plus 4y squared dA, where S is the region I mentioned earlier. So it's the set of all points x, y, such that y is greater or equal to 0, and x squared plus y squared is between 1 and 4. Okay, so we saw that earlier, so it looks like that. This is S. Okay, now let's say you never heard of polar coordinates. You could set up the integral. It's nasty, but you can. You'll have to chop up the region S, and you're going to get integrals where you have to use 3 different kinds of trig substitutions. It's not easy, okay? But if you do it in polar, it's actually pretty easy, okay? So we use change the polar coordinates. Okay, so we know that S can be described as follows. Hopefully you can see this by looking at the picture, right? So the angle goes from 0 to pi, and r goes from 1 to 2, right? So this integral, by our theorem, what is it? Well, integral 0 to pi, integral 1 to 2, right? So 1 and 2 are the h1 of theta, h2 of theta. They happen to be constant. That's the easiest case, okay? Then what do? I replace every x and y by r cos theta, r sine theta. So that's 3 times r cos theta plus 4 times r sine theta squared. And now don't forget, you have to multiply the whole thing by r. This is absolutely crucial. It's crucial because that's how it is. So if you don't put the r in, you'll get it wrong. But in many cases, the r is actually helpful in the integral. If it's not there, you might be staring at something that you can't integrate, because a lot of these problems are rigged for you to be able to do them, right? Okay. So I need to compute now this integral in r and theta, okay? So let's do that, because we'll review a couple of little things that you should know, okay? So let's just multiply this out. So this is 3r squared cos theta plus 4r cubed sine squared theta dr d theta. Okay, so my first integral is the inside. Can you just repeat quickly? I was lost. Why the r is from 2? Yeah, so x squared plus y squared is between 1 and 4, right? So x squared plus y squared equals to 1, the circle of radius 1. X squared plus y squared equals to 4, radius 2, right? It's good. Okay, so this is what I need compute. Okay. So I start with the inside part as usual. So I'm integrating with respect to R. That's easy. Could the order of integration be changed, or do we have to start at the variable? Good point. In this particular example, you could switch them. Absolutely. Because it's a rectangle. So the bounds inside are constant. So you could, if you wanted to, yes, you could switch them. But of course, you switch everything, right? So you have to be careful to keep the bounds with the right variable. Okay. All right. So I'm integrating with respect to R. So this will be R cubed over 3 times 3. So that's R cubed. Cos theta is a constant. Plus 4R4 over 4. So that's R4 times sine squared theta, which is constant. That's between 1 and 2 u theta. Right? I could add here, Marie, that you could do it, but you're not going to gain anything. I mean, it's there. The two integrals will be either direction are going to be of exactly the same difficulty in this particular example. Okay, so let's just substitute. So this is integral 0 to pi. I substitute, that's 8 minus 1. I'll do it just in one shot. That's easy. 7 cos theta plus 15 sine squared theta. Okay. Now, little refresher. So the next 3 examples will look a bit the same. It's sort of a fluke, although it's obviously, I mean, once you go to polar, you're obviously going to integrate cosines and sines a lot, right? So, so our little refresher on integration of even powers of cos and sine, right? So you remember, if you have an odd power, that's pretty easy because you can factor out one of the factors and use it as your derivative and do a substitution. But if it's an even power, you have to use an identity, right? So what are these identities? If you're like me, you don't remember these things all the time correctly or at all. So you try to remember a few things and get them back from that. So what I do remember is this, is that cos of 2 theta is cos squared theta minus sine squared theta. It's beaucoup moins ici. I don't know if I've mentioned this before in Cal 3. Anyway, so from this, what do I get? If I want to rewrite sine squared, I'm going to write this as follows. This is 1 minus sine squared minus sine squared. So this is 1 minus 2 sine squared. And this gives you that sine squared theta is 1 minus cos 2 theta over 2. And similarly, you can get cos squared theta. This is 1 plus cos 2 theta over 2. Okay. Yeah, even though you're doing your test at home, I will include a sheet with some basic trig identities, just because, why not? Okay, so these are the 2 identities that are useful when you're integrating even powers of cos and sine. Okay, that's the way you do it. Okay, so if I go back here, this will be the integral 0 to pi 7 cos theta plus 15 over 2 times 1 minus cos 2 theta. Okay? And from there, it's straightforward. Okay, so I'm integrating cos, derivative of sine is cos, so this is 7 sine theta plus 15 over 2. Integral of 1 is theta. And again, derivative of sine 2 theta is cos 2 theta times 2. So then we'll have a 1/2 of that. And this is between 0 and pi. Okay? So I did a quick little substitution there for the last one. Okay? So this was what I need to evaluate. I'll just paste it here. Okay? And so I evaluate this at pi and at 0. Now sine of pi and sine of 2 pi and sine of 0, they're all 0. So all these guys disappear. So we're left with 0 plus 15/2 of pi minus 0 minus 0 plus 0. So we get 15 pi over 2. Let me check that. Yes. Okay. So far, so good. All clear. Excellent. Okay. So let's go to another. All three examples are a little bit of the same flavor, so this might help. Second example. Find the area of one leaf of the 4-leaf rose. Okay, so a couple of things here. If you remember, we have a formula to find the area of a region using the double integral. So what do? You look at your region, you look at something of height 1 over it, so the volume of this thing will be 1 times the area, which is the area, right? So the area of S can be computed as the double integral of 1 over S. Okay. So now, what is the description? So in fact, this here there's something a little less. Let's do that again. It's a bit easier than the previous problem in the sense that here you don't have to ask yourself, do I go to polar or not? There is no other way because the only description we have of S is in polar. So you have to switch to polar coordinates. So that in a sense makes it easier. Okay, so again, what is S? We saw it earlier. It's the set of all R theta such that theta is between minus pi over 4 and pi over 4. And R is between 0 and cos 2 theta. Okay? So we switch to polar. Be careful, right? The formula we saw is in rectangular, dA, it's rectangular coordinates, so you have to switch to polar, okay? So this, when you switch to polar, what is it? It'll be the integral from minus pi over 4 to pi over 4, 0 to cos 2 theta, And now you replace every x and y by r cos theta. R say, since, geez, by r cos theta and r sine theta. There are no x's and y's here, so there is nothing to replace. It's just 1, but you must multiply by r. I am sorry, I am very tired, as you are probably also. So this is r, dr, d theta. Okay, so this is the integral we must compute. Now here, if you ask, can we flip them? No, it's not possible because the bounds for r are not constant. We cannot switch the order of integration. That's verboten. Okay, so let's do this integral. Integral minus pi over 4 to pi over 4. What is the integral of r with respect to r? R squared over 2. And I'm going from 0 to cos 2 theta, d theta. That's ugly. That's better. Okay. So let's copy this, right? Let's paste this. Okay, so I just replace and subtract. Integral minus pi over 4 to pi over 4. This will be cos squared 2 theta over 2 minus 0. So this is it. Okay. So I have to integrate cos squared. I can factor out the 1/2. Right? I have an even power of sine or cos. I use the identity to decrease the power to 1, right? So what is cos squared of 2 theta? If you look at this little identity, is 1 plus cos of twice what's inside. So here will be 4 theta over 2. I'm going to use that. So this is 1/2 integral minus pi over 4 to pi over 4 of 1 plus cos 4 theta over 2 theta. Okay, I'll factor out the 2, 1/2 I should say. So this will be theta plus, so derivative of sine of 4 theta is 4 cos 4 theta. So that's 1/4 sine 4 theta. This is between minus pi over 4 and pi over 4. No, I am not drunk. Maybe my bosses are watching this on YouTube right now, so I'm all fine, thank you. Okay, so far so good? Yep, all right. Okay, so let's just substitute in here. So 1/4 pi over 4 plus, well, sine of 4 times pi over 4 is sine of pi, which is 0, and the same for the -1, so that's just gone. And this will be minus pi over 4 plus 0. So this is 1/4 of pi over 4 plus pi over 4. So this is pi over 8, which is kind of cool. So the 4-leaf rows, each leaf has area pi over 8. All right. We're good for one last example. Here we go. Last stretch. We've run 40 kilometers, 2 kilometers left. We don't stop now. Here's our third example and final example. So we're asked to find the volume of the solid that lies under the paraboloid z equals to x squared plus y squared above the xy plane inside the cylinder. X squared plus y squared equals 2x. That looks complicated. Okay. Now, if you can draw this, yes, I'm sure. Thank you for putting it in writing. I'm just, well, I'm all alone here just talking to my computer, so, you know. Yes, I'm sure. Thank you. Okay, where was I? Yes. Yes, I'm good. I'm good. Yes. I don't know why I start talking with accents. It's just I'm boring myself, so I just try to. Okay. Yes. Thank you for your concern. I'm good. Thank you. Okay. So we have a paraboloid. We're looking for the volume of what's under it, above the XY plane, inside a cylinder. Okay. Now that looks complicated until you realize, well, you look at the cylinder, look at its equation. What's missing is Z, and that's really good news, right? Because it means that your cylinder is vertical. Okay, so no Z in x squared plus y squared equals to 2x. So the cylinder, well, is vertical, right? It's something like that. So basically being inside the cylinder just means being above the disk where the cylinder meets the XY plane, right? So inside the cylinder is just misleading, means above the region in the XY plane, inside the cylinder. You see what I mean, eh? So you don't want to try to draw this. It's actually a very strange looking solid. Well, it's like you take a cylinder and you cut it with a paraboloid. Like, it actually looks very nice. And it would be nice to make it out of stainless steel. But basically, we're going to do the double integral of that paraboloid, x squared plus y squared, over that disk, that region, right? So I have to figure out what this region is. but this might look familiar, right? So x squared plus y squared equals to 2x. That's the same thing as x squared minus 2x plus y squared equals to 0. You complete the square, and you're going to get x minus 1 squared plus y squared equals to 1, right? So what is that? Is that, right? So this is the circle of radius 1, centered at 1, 0, right? Right? So the cylinder is just the extension of this circle in the z direction. So we're going to integrate. So for the volume we're looking for is the double integral over s of x squared plus y squared, where s is this, right? Okay, but now, I mean, you can try it rectangular, but it's actually pretty bad. So, because you're going to get square roots, and I mean, you'll have to do a trig substitution in there at some point. But let's just go to polar. We're going to switch to polar. We do have a polar description of this, which is actually decent, right? So recall that S has a nice description in polar coordinates. Okay, so I'm going to it's water, I swear, and I'm wearing pants too. Okay, so what's this description? If you recall, the description was the following. So the curve is given by r equals 2 cos theta, and the angle here will be going from minus pi over 2 to pi over 2. You have to be careful that the angles you choose are the ones for which r is positive. Okay, so minus pi over 2 to pi over 2, and r is between 0 and 2 cos theta. Okay, so double integral over s of x squared plus y squared dA, that's rectangular coordinates. We switch to polar, so this will be integral minus pi over 2 to pi over 2, integral 0 to 2 cos theta. Now I substitute every x and y by r cos theta, r sine theta. But what is x squared plus, I mean, you can do it, but what is x squared plus y squared if you do that? I'm waiting for an answer. Not 1. Marie, you're almost there. Very close. Maybe you wanted to type a 2 rather than a 1 there. Right? If you remember, when x is r cos theta, y is r sine theta, what is x squared plus y squared? It is r squared, right? Which makes sense because if you square r cos theta and you square r sine theta, you can factor out the r squared and you'll be left with cos squared plus sine squared, which is 1, right? So it is r squared. Okay, so this is r squared when I substitute x and y. You can do it full length if you prefer, right? Okay. Don't forget, you need to multiply the whole thing by r. Do not forget that. Okay? All right. So, is that okay? Like Elliot Smith used to say. Say yes. Yes, yes. All right. Okay, so this is, then I'm going to integrate r cubed. So this is the integral from minus pi over 2 to pi over 2. R cubed, that's r power 4 over 4 between 0 to cos theta d theta. Not so bad. Now it's going to be a little uglier, but it's not too bad either. It's just you have to go through it. So now I substitute 2 cos theta in there, so that'll be 16 cos power 4 theta over 4 minus 0 d theta. Okay, we're almost there. Okay. So this is what I need to compute. So this is the integral minus pi over 4, sorry, pi over 2 to pi over 2. I'll factor out of 4 cos power 4 theta d theta. Even power of cos. What do? I use cos squared theta is 1 plus cos 2 theta over 2. But it's a power of 4, so I'll have to do it twice, basically. So what I'm going to get here is 4 integral minus pi over 2 to pi over 2 of 1 plus cos 2 theta over 2 squared. Right? Cos power of 4 is the same as cos squared, all squared. So 4 integral minus pi over 2 to pi over 2. Expand the square. 1 plus, plus 2 cos 2 theta plus cos squared 2 theta divided by 4. Right? Let's cancel out those 4s. And this is 1 plus 2 cos 2 theta plus cos squared 2 theta. Like that. Okay. I can integrate, I can split it up as a sum, but I'm still stuck with an even power of cos, so I use the identity. Once again, I'll do it immediately. So this is the integral minus pi over 2, pi over 2, 1 plus 2 cos 2 theta plus, and again, here's cos squared of, why do you have 2 cos 2 theta? When I squared, so yeah. That's fine. Okay, so now I switch my cos squared to theta, which will be 1 plus cos 4 theta over 2. right? So the inside of the square cos gets multiplied by 2, okay? And now I can integrate. So this will be, it's just the same as the 2 previous examples. So theta plus sine 2 theta plus 1/2 of theta plus 1/4 sine 4 theta. And all this between minus pi over 2, pi over 2. Okay. Now, once again, I mean, these problems are very, very similar. It is a fluke, but again, you expect this kind of thing to happen when you're doing polar coordinates. But again, sine of pi minus pi, 2 pi minus 2 pi, they're all 0. So these all disappear. So we're left with pi over 2 plus 0 plus 1/2 of pi over 2 plus 0 minus pi over 2 plus 0 plus 1/2 minus pi over 2 plus 0. Okay, I just replaced, subtracted. So here's what I get. So what is that? Pi over 2 plus pi over 4 plus pi over 2. That's minus pi over 4 plus pi over 4. So that's 3 pi over 2. I mean, if you take a step back and you look at what we just did, we have this paraboloid that's going inside a cylinder, which is off the origin. And we computed the volume of this thing pretty easily. I mean, I've done it by hand. I didn't need a computer to do it. And it's not like I had to use all sorts of very deep stuff. I mean, we've reached that deep stuff by ourselves, right? That's pretty cool. It's pretty good. Any questions? It's all good. You're the best. Okay. So this is the end. To go back to the example of the 4-leaf rose, can you use any other angle that make one leaf to get the same answer? Okay, let's go back there. Okay. So your question is, can you use any other angle that make one leaf to get the same? The only thing, yes, you should get the same thing. Just remember when we did this, right? When we sketched it out, when we went from 0 to pi over 4, r was positive. Then when we went from pi over 4 over there, then r went negative, still negative, then positive. So you have to be very careful how you do it to make sure that the r that corresponds to the angles you're using is always positive. That's the only thing you have to be careful with. Okay, so I'm not sure that in all, maybe, I think maybe if you use these angles, you should be okay. I think r is positive. If you go from 3 pi over 4 to 5 pi over 4, I think you're okay. But if you use angles where r is actually negative, you'll be canceling out stuff. It's bad. It doesn't work. You see what I mean? Okay. So the simplest one, I think, is the one that we use. Okay. Okay. So this is the end of the official material for Cal 3. So what's left? We have Monday, and then we have Wednesday, which is our test. And there's parallel to this, there's the WebWorks that closes Tuesday, I think. Okay. It's good practice for the test, right? It's really focused on integration, everything we've done in integration. I've noticed that very few of you actually use my sessions where you can ask questions. So what I'm going to do on Monday, it'll be optional. You don't have to be there. It's not going to be material on the test, but I will do a couple of things which are cool. So it's completely optional. You don't want to be there, don't be there. If you want to ask questions, be there, okay? But I'll talk about the Gaussian curve and possibly about a fantastic paradox about volume. Okay, so again, if you don't want to be there, don't be there. You can watch it later on YouTube. But I'm going to talk about these things and answer questions. That's Monday. Wednesday is the test. So that's it. Yeah, I'm going to send you that in just right when I finish the meeting. So the question is, what are the exact sections from chapter 4 that will be in the exam? I'm going to send you the exact contents of the exam right after this by Neil. Are you going to send extra problems or the class examples are sufficient? If you look at the problem list, you have tons of stuff. I can look if I have other stuff, but there's tons of examples. I mean, the list of problems has a lot of stuff. You should be fine. I'll look up if I have extra things. I'll send them out, but we have the WebWorks and the list of problems, so you should be good. All right. Okay, so if there are no other questions, I bid you farewell, good people, and I'll see you on Monday if you wish, and if not, goodbye, take care. Thanks. Yes, Fubini the magician. Yes, I like that. Thank you. It was fun having you.